Hello everyone, welcome to Easy Physics again. Today we are going to continue with the AC circuits and we will learn generators, and again we will use teaching with reasoning. The learning objective for today's lesson is you are going to be able to describe the process of alternating current generation, and you are going to see how we are relating the generation of the current to the electromagnetic induction. What is an AC current source? A generator is an AC current source. What is a generator? It's a device that transforms mechanical energy into electrical energy. And a generator consists of a coil of wire which is rotating in a magnetic field. And the Faraday's law of induction is inducing the oscillating voltage in a generator. What is the Faraday's law of induction? Faraday's law of induction says that a voltage is induced in a conducting loop if the magnetic flux through the loop changes. So I will describe it with an animation. We will see how a voltage is induced when the magnetic flux is changing. Okay. So let me have my simulation. Actually, it's not mine. Here is a coil. And here's a magnet. There is magnetic field lines around the magnet, and now the magnet is stationary, coil is stationary. Here a lamp is connected to the coil. Now I'm going to move the magnet toward the coil. As the magnet is going to move toward the coil, the magnetic field here where the coil is placed is going to change, and which will produce some induced current, induced voltage, and our bulb will light up. Let's see. As you see, as I move the magnet toward the coil, the bulb is lighting. So once, if I stop, there is no lightening of the bulb. As long as the magnet is moving, which changes the magnetic flux through the loop, and which it in turn, as we learned from the Faraday's law of induction, it produces some voltage, and this voltage is lighting the bulb. Okay, let's return to our presentation. What are the components of an AC generator? In an AC generator, we have two magnets. As you see here, we have two magnets, N pole and S pole of the magnets are facing each other. There is a coil. Here only one turn is shown. There's a coil here and it has two legs. Here we have two slip rings. One of them is this one and this is the other one. Two slip rings. And there are two brushes. And this is a handle. So we can rotate this coil with turning this handle. But generally we are not using our hand. We use the power from the wind, from the water, from solar power. So we can rotate this coil with natural energy sources. Then we can get electrical energy. Okay, let's continue with the generation of the current in a generator. So as you see here, again we have two magnets, and a coil is inserted in between the two magnets. There is magnetic field lines. They are shown with blue lines. Here is the coil. Okay, so again the coil has two legs and they are touching these slip rings, and one of them is touching this slip ring and the other one is touching the other slip ring, and these two slip rings are touching the brushes. As this coil is rotating, the magnetic flux here, the magnetic flux is going to change. So what is magnetic flux? Magnetic flux is the B times magnetic field times area times cosine of theta. Magnetic field here in between two magnets is constant. The area of the loop is constant again, and what is changing is the theta. So the theta is the angle between the magnetic field lines and the normal of the surface. Normal of the surface of this coil. As the coil moves, as it rotates, this theta will change. Sometimes when the coil is perpendicular to the magnetic field lines, the theta is going to be 0, and sometimes it's going to be equal to 90 degree, 270 degree, 360 degree. As this one rotates, the flux will change. So the change of flux, according to this Faraday's law according to this Faraday's formula, as the flux is changing with the time, an induced electromotive force is going to be produced. So a voltage is going to be produced, and this voltage is going to be a changing voltage. It's a sine function. As you see, it will have a zero value, then it will be increased to a maximum value, and then zero, and then minimum value. It completely depends on this formula, and in this formula the flux change depends on the angle change. So as the angle changes in this arrangement, the amount of the voltage produced is also going to change. So this is the source that we use in alternating current circuits. Let's look at an example. It will help us to understand the topic better. A coil consists of 200 turns. Each turn is a square of side 20 centimeters, and a uniform magnetic field is directed perpendicular to the plane of the coil. If the field changes linearly from 0 to 0.5 Tesla in 0.8 seconds, what is the magnitude of the induced electromotive force? So let's solve it all together. As we know that the induced electromotive force E is equal to negative n times delta phi over delta t. Okay, it will be equal to negative n times delta B times A over delta t. And here in this question, the area is not changing, and the magnetic field is changing from 0 to 0.5, and the number of turns are not also changing. So I'm going to write n times A delta B over delta t. So then the induced electromotive force or voltage will be equal to what? I'm not going to use negative sign here. We are asked to find the magnitude of the voltage. Okay, so we have 200 turns times, and one side is 20 centimeters, so the area will be 0.2 square of 0.2 times, and the change of magnetic field is final value is 0.5, initial value is 0, and it changes. This changes takes place in 0.8 seconds, and if we do this calculation, it will be 5 volts. Now I have two multiple choice questions for you. I will not answer. You can find the answers at the bottom of the video. Please read the questions and provide your answers to these two multiple choice questions. Here is the first one, and this is the second question for you. Please provide your answers at the bottom of the video also, if your answers are different than mine. So thank you for listening. See you next time.